2, 1.
Hi YouTube, this is the Data Science Learning Community book club on Introduction to Statistical Learning in Python, and we are now up to chapter 10 on deep learning. So what I'm going to do in this session is run through the first half-ish of the chapter up until about section 10.9, at which point it gets marked with the difficult car up the hill logo. And yeah, so I won't go into this stuff about backpropagation and whatnot, but I'll hopefully skim through the rest up until then. Okay, so I've just taken notes in Obsidian basically, and I'm just going to talk through them. As usual, please do jump in and discuss this with me as I do it. So yeah, we're talking about deep learning, and the foundation of that is neural networks. And so the chapter starts out describing what a neural network is. It has this great line saying that they're excellent on niche problems like image and video classification, speech and text modeling, which I think, given the boom in machine learning and AI in the past 2 or 3 years, I think sounds like quite a funny a funny comment to make. That I don't know if you still would. It doesn't feel niche anymore. It feels almost ubiquitous when people are using ChatGPT to solve every problem rather than niche problems. So yeah, that's something we just discussed. Actually, I'll mention now while we're recording is that the book was written a few years ago, although this version came out in 2023, so it doesn't cover, this chapter doesn't cover things like, Jack's put in the chat that I nearly solve every problem, and that is quite right. The uncertainty is not well captured in these models. Yeah, this book came out a few years ago, so this chapter doesn't cover more modern machine learning, things like attention mechanisms, transformers that's been caused the boom in large language models that we're seeing. But it will teach us the basics. Okay, so the chapter is focused mainly around CNNs, so convolutional neural networks, and RNNs, recurrent neural networks. But yeah, I wrote this joke here because it seems like anytime you read anything about deep learning, it's only a matter of time until you see the MNIST data set come up. And indeed we do. So this is the first figure that I've made very large, basically describing what a neural network is. So you have your input data on the left, or your features, these X's as it's been throughout the book. And then you've got a hidden layer in between that does some magic and produces your output f of X, which then gives you output Y. And what the hidden layer does is computes what they call activations, which is a nonlinear transformation of the input data. These are called hidden layers because you don't directly observe them. You only know the X going in, the data going in, and your output Y or f of X in this case. And the output is just a linear combination of these hidden activation layers. This is a feed-forwards network with p equals 4, so that p is the number of features, which is, so we've got 4 X's on the left, and you've got 5 units in the hidden layer, and you've only got 1 hidden layer. And we'll see later on, these get much longer, surprisingly longer, and can also get deeper. You can have multiple hidden layers. Okay. Yeah, and the basic gist is that a neural network tries to build a nonlinear function f to produce or to predict this response y. And the model has the form, you can sort of work it out here, running it through to get this form of the output. And so you can see how it's a nonlinear function of the f's. I think what I'm surprised at this point is at least this architecture is relatively simple, and you still see very surprising performance. But yeah, because of the number of parameters and the amount of data that you can put into these things. But it is just a nonlinear combination of the inputs. Yeah, the key here is these G functions, which are activation functions, which the reason they're called neural networks is it tries to model like a neuron in the brain. And you can think of the activation function as being like the level of electrical impulse that you'd have in a neuron that would cause that neuron to fire. It's the same here. Is there enough coming from this term here I can't highlight, to activate this node that this then contributes to the final output. So these activation functions generally look like some form of step function, which I think we'll come on to later. Yeah, my sort of first question is, how many parameters are there in this model here? If you've got 5 hidden units, 1 hidden layer, and 4 features. This is a counting exercise, but I think it's quite informative. Just pause for dramatic effect before I fold it down. Or does anyone want to try and contribute an estimate?
Wait, is it not just a multiplication?
Yeah. I don't think it's a direct multiplication, but it's close.
Can't spoil us.
So yeah, there's k plus 1 betas, because you've got beta naught, and then you've got k betas, and then you've got p plus 1 w parameters, because you've got p of them here, another one there, and you've got k lots of them in that sum. So you have this many in total. So in this case, you have 31 parameters, was my estimation, but then I wasn't sure because I was trying to work this out by counting the number of lines in this diagram as a proxy for the number of parameters. And I only counted 25 lines, but I think that's because I'm not including the intercept terms there for each stage. So that gives you the 6 left over to give you the 31 parameters. So yeah, straightforward model in terms of logic, but has a lot of parameters in it, potentially compared to things we've seen earlier in the book. Okay, so activation functions, as I mentioned earlier, you're looking for something with some sort of step in it, or that starts at 0 and ends at 1. Not necessarily a non-linear step. Traditionally, sigmoid activation functions were used because they're nice and smooth. But the problem is there that they're quite expensive to calculate, because you've got exponentials, you've got fractions of exponentials, and so what's used more commonly now, another common one is like a hyperbolic tangent function. You might call that tanh or than, depending on where you learnt maths. But yeah, we also have these ReLU functions, which is rectified linear unit, which is 0 if you're if x is less than 0, and then goes up linearly. So it's equal to x if x is greater than 0. And they're more favored in modern architectures because they're very quick to calculate. And you can also build into your GPU or your CPU things that calculate that even quicker. So you're getting close to bare metal and evaluating that rather than having to evaluate sigmoid functions. Yeah, so the activation functions are key. If these G weren't here in this equation, this would just be a linear model in X. So they're really, yeah, the key to this approach. Jack, did you have a question, comment there? So you.
No, I'm just gonna say, like, so say with like sigmoid versus ReLU, you've got the like computational cost, but you've also got like a sigmoid can take negative values and like put them into the 0 to 1 space. So like a -3 could still have a positive value, whereas ReLU will basically go, if anything, if it's like a negative score coming out of the say that layer, like the linear combination that's led to that layer, if the score is like negative, then, or if it's 0, then the output of the ReLU is going to be 0. So essentially, like negative scores just get dropped, like they don't pass through the network. Whereas with sigmoid, like negative scores get like recapitulated into that 0 to 1 like bracket, from my understanding. But I was just going to clarify whether that was what other people are kind of like aware of as well.
I see. So you mean that they're passing some information on somehow for the negative values as well, rather than just ignoring that?
Yeah, like in ReLU, they're not doing, like, if you don't do that, you lose any like negative scores, you just drop them. They can't be passed through, just equivalent to zero. Whereas in sigmoid, you can pass the negative stuff through.
Yeah, okay, so that's as demonstrated by this diagram that you've got the green line that's positive for z less than 0.
Yeah, and it's like, I think they may even say in the book as well, it's like if it is positive, you just take the value. Like that's just what comes out. It's either 0 or the actual value, depending on whether it's positive or 0 or negative.
Yeah.
I wonder, I like it wouldn't, it's not, so that's something I'd say I've probably been aware of for like a long time in the past. I don't, it's kind of always hard with neural networks to think like, what does that actually mean happens to like your ability to predict the inputs or outputs? Like, is that beneficial to you for some reason? It's always, in my mind, it's always hard to even consider why or how like that would be the case as the signals are like propagating through the network. Is like, why did ReLU, and the modern ones are like generalized version of ReLU and other things, but like they tend to be similar to ReLU. That's maybe, it's maybe a bit deeper. Oh, sorry, go on.
I think that's a question sort of throughout deep learning and machine learning, is how you don't really have, I feel like your intuition doesn't play as good a sense as it in other parts, because the models aren't that interpretable. It feels like we've just tried a bunch of things and some of them work better for some sorts of problems or work faster. Yeah, because I guess the intuition here is that the sigmoid function, your intuition would that it would be better, like you say, retaining some information, but the trade-off in computational efficiency isn't, that information isn't worth it, because you can train the ReLU on bigger models, or you can train it for longer, I guess. But yeah, I certainly don't have that intuition in machine learning and deep learning to know a priori what might work and what won't.
Yeah, I suppose there's also a sense of like the regularization, because you've got so many parameters and you might not always have so much data. This is just speculating. I wonder if there's something about the ReLU part that plays like a little role in just like smashing away some of the weights and information for you, which is potentially quite nice. But you, as we get into later, so you do also have like explicit parameters for other ways of like regularizing. So that might be complete nonsense.
So it's just ways of trying to increase sparsity in the network, I guess. Increase the zeros in some sense, because that makes it easier.
Yeah, I suppose you like focus on the high scores, or like, and you would say more in the not more, but you would in the sigmoid more than you would the lower scores, because they have a higher value, obviously. But like in the ReLU, it's like it's only the positive or the high scores. But then that also feels kind of weird to me, because it's like sometimes it's really useful to know that stuff is like negatively correlated, right? Like if you're going to predict stuff. I don't know. I don't necessarily have a good intuition for it, but I was just clarifying if that's what other people take as well from at least the activations that they outline in this chapter.
But if the correlation was negative, wouldn't your weight just become negative, and then your activation would still be firing? Because then you'd turn the negative correlation into a positive with the negative weight. I don't know if that's true. That's just a guess. And then the neuron is still firing.
So but say like the activation is like looking at the score in the lane. If that's negative for the ReLU, that's what is the input into the ReLU. And then if that's negative, it's just like gone. You wouldn't, I don't think you like multiply the negative with a different negative. Now you've got a positive. Is that like what you mean?
Yeah, from here, these weights could be negative. Maybe I'm misunderstanding your question or the architecture here. Is your question stated another way, like, can can models fit negative correlations? Which seems like a yes.
Yeah, there must be a mechanism for them to do it.
Yeah, I think it's just rather than it's not negative values, it's you're trying to measure the amount of information, I guess, that input provides to the output. And so there's no such thing as negative information.
Yeah. It's not it doesn't exist. Yeah.
That doesn't work for sigmoid, I guess. That argument doesn't work why a sigmoid would work.
Yeah, well, it's taking the scores, like that. So the single layer case is always kind of really weird to me because I'm so used to thinking of like having like a weights matrix or something where you take the inputs and then multiply them with like the weight matrices, and then that like you got your dot product or whatever, and it's like an affinity score between the input and the weight matrix. And you basically then say when the value is negative, you're like saying there's just like no affinity between this input and that particular part of the weight matrix. So like basically just don't do anything, like just pass on and let the ones where there is an affinity, let all of the signal go through that. But in this like single layer sort of case, like I guess we do have our weights.
You've still got a weight matrix, it's just one, well, it's a vector.
Yeah, I wonder what's maybe just a flag, not to dwell on it, but what, how do negative correlations get captured? And it's probably a case of just doing some of the calculations by hand and just seeing like what actually happens. How do they get captured and what happens in the hidden layer and then what's passed on to like the output or the function that generates the output? I'll just put that in Slack.
I don't think I've read enough on the training section to be able to like answer that, I guess. But I guess your weights would just become negative, and so your gradients would be. I don't know. I'm not going to hypothesize anymore. Okay, carrying on. Yeah, so for a quantitative response, so if your output y is a number rather than a classification, we typically use squared error loss, which we've seen quite a lot already. So you're choosing the parameters to minimize the difference between your f of x, your learned function, and y, your true value, or the value in the training data rather than true value. Of course, one hidden layer is cool and you can do a lot with it, but we can just keep adding more. And using multiple hidden layers of modest size gives better performance. Oh, I'm hiding an answer there. Using multiple hidden layers of modest size gives better performance than one really big hidden layer. And they illustrate that using MNIST. Ding, ding, ding. There we go. We got 29 lines into our notes before we hit MNIST. So for those who haven't seen the MNIST data set before, it's a data set of images, and all of the images are handwritten digits. And the goal is to say what number that is. So you obviously exactly what you do when you scan in your check, that's what's happening. They're trying to detect what numbers you've written in the balance so that they pay you in the right amount of that check. The MNIST data set, I think, was just based on like college students who they got to write loads of numbers. But every image is 28 by 28, so 784 pixels, which isn't that big. And each of the pixels is an 8-bit value between 0 and 255, which basically is from white to black. So that's how much of the drawing is in that square, if you like, in that pixel. That gets stored in a big input vector. So you just get you like flatten your square image into a vector that's then 784 long. And the output is this time a class layer. So rather than having a quantitative response, you've got classes 0 to 9, where 1 in the ith position in this vector is the i-1th label. I've probably got confused here between Python numbering and counting from 1. And this is what we call a one-hot encoding, and you'll see this quite a lot in this chapter and also in machine learning, where you've got a vector filled with zeros and one of the elements is 1. So one of them is hot. In the MNIST data set, you've got 60,000 training images and 10,000 test images. And this is an architecture that works well. So you've got 2 hidden layers. And the first hidden layer has 256 units in it, and the second hidden layer has 128. Then your output layer, of course, has 10 units. And the W's here are our weights, same as before. And my question here was that I don't think the book answers, but is why does this architecture work well? As a practitioner, why would I think to design my network like this? Or why is it better than others? And how was that discovered? I don't know if anyone has any thoughts or answers to that question.
Just to clarify the question, when we say like better than others, do you mean better than other neural network architectures, or like other, like the traditional approaches that we were looking at?
Better than other neural network architectures. So in the context of the chapter, we've been shown a single layer one, and now we're just, it feels slightly out of the blue that they're like, oh, and for MNIST this works. And I was like, wait, why? Why would I choose 2 layers? Why would I choose 256 units in the first hidden layer and 128? Like, is that something you just brute force, or is there a reasoning behind that?
It's an interesting question, because like, say if you like skip a step and you go on to convolutional neural networks, and once you like kind of get how they work, it's really easy to phrase an answer in terms of like what the actual representations are at the lower levels and how it helps to like recognize images at the higher levels. But you don't really have any way, or I feel like you don't really have with these multi-layer, like just with hidden layers, you don't really have any way of making sure that the hierarchy, like the features that are pulled out in the hidden layers, follow like some nice hierarchy. It's kind of just whatever features are eventually good to predict, like that's what you get in your hidden layers. So it's kind of weird, because I've seen other, say, hidden layers where you have maybe like you got your first layer, and then you've got a hidden layer that's quite small, and then you've got a larger hidden layer, and you've got another hidden layer that's quite small. So you've got like quite a compact representation, then like this other representation that's much bigger, and then you go back to a compact representation. And it's like, yeah, maybe it works, but you don't like know why. And then sometimes you're just taking like, let's have 768 dimensions in like layer 3, and let's just have like 212 in layer 4, and then maybe we should have 12 at the end. And it's, I don't, in like architectures like these, it always has, to me, always felt like a bit of sort of hit and hope kind of structure, rather than like, oh, it actually makes sense for the problem. But that could be my ignorance more than anything else.
Yeah, I think you raised an interesting point there about the small, like small, big, small, I'm going to call it, of how that can even work. Because I sort of view this as like a funnel, right? You start with too much information and you're trying to sit down to your output. But then how does your funnel get wider again, and why does that work well?
Yeah. One thing I would maybe it helps to think about, and I don't know if it's like expressly stated in these terms, but like kind of the great thing about neural networks, if you're the researcher, and it's also kind of the bad thing, but like the great thing is that you don't have to do a bunch of feature engineering. Like you don't have to sit, explore your data loads, like come up with a feature, like look at loads of graphs and be like, okay, that's a good feature. Let's like put that in. You've normally got like your inputs, some kind of like token or whatever. And then the network, if you give it loads of space, like parameters, it's basically just going to make loads of features. And some of them are going to be rubbish and some of them are going to be great. And you're not really going to like know what they are or anything, unless you do really like deep interpretability work. But you're for most practical purposes, you're not going to have a clue like what the features it's finding out are, which is like a nice thing.
I think that's a really nice way of putting it. You're like, you don't need any domain expertise to get a good output, but equally, it doesn't really give you any domain expertise because you can't say the why of that.
Yeah, what should happen is the domain expertise is all has to be kind of like put back into the pipeline at the data set curation stage. Like someone needs to make sure you're getting the right data for like a network, and you've got some kind of processing step to like take something that is not numbers and make it numbers. But if you can just do that, if you can get a really good data set, usually with the help of a domain expert, like once they've given you that data, you don't need to know anything about it pretty much. Like you just computer goes brr and it sort of works. But one I would say about the smaller big small is like layers. It tends to be the case that even though it doesn't like show it here, like layers can skip in modern networks. So like layer 2 can communicate with like, so layer 4 can communicate with like layer 1 or like layer 2 or layer 3. So if you force it into a really compact representation, and then you go to the bigger ones, it's like the signal can still propagate through the other layers to the later layers. But when you force it to focus on a small compact representation, you force it to focus on the really important stuff early. But then it's just mind-boggling to think about what's actually happening.
You've just clarified something for me there. That's why these are feed-forward neural networks. I don't think the book makes that explicit of what is not a feed-forward network.
Yeah, so there's feed-forward is just like you're just passing like the from one layer to the next layer and stuff. But later there's an innovation about like it's called residual something. But that's how through the residual pathways how like later layers can connect with early layers. With like an RNN is an example of a network that's not feed forward. Like I think feed forward is maybe just about the amount of computation that can happen, like because RNN will allow it to like loop around, whereas feed forward will be like stuff just goes bang, 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 bang through, and no loops.
Okay,
It's probably beyond the scope here.
Yeah. Anyway, back to my question. Why does this architecture work well, or why is it better than others? So for me, the thing that stuck out was that these were both powers of 2, 256 and 128, and I thought that's probably not a coincidence, and that's probably not anything to do with the problem itself. There's probably more of a computational benefit. So I think it's the balance between computational complexity and accuracy. I've summarized quite a lot there by saying computers like powers of 2. And two layers outperforms one massive layer. But adding more layers gives you more complexity without improving the accuracy. So it is quite heuristic, but I think the heuristic in mind shouldn't only be how well does this model fit the data, but also how computationally costly is it going to be to fit this model, because that's a key problem in oh, there you go. Why are both K's a power of 2? I think I've merged my 2 questions there. I don't know. It's like the powers of 2 was my answer. So this network has 235,146 parameters, or weights, as we're now calling them. Feels like you've stopped being a statistician at this point and really moved over to machine learning when you start calling them weights instead of parameters. And what I was doing here was just checking whether it's any different to what we calculated earlier on and the formula we calculated earlier on for a single hidden layer. And it is, because you've got 2 hidden layers, but you can run exactly the same calculation to work it out, which is what happens here. And miraculously got the right answer on my first go. But it is just a case of multiplying and adding the sums that are going on there. Yeah, I think where I've put things in italics is quotes from the book that I didn't quite understand. So it's, if these were all separate quantitative responses, we would simply set each fm to x to equal to zm and be done. I think the Z here is just the output. What was Y before? I don't know whether there was a change somewhere that I missed that turned it into a Z. Yeah, but what I was misunderstanding here is that this F that you apply at the end, they're saying you would basically just set it as the identity function and it would come out with your answer. But we're not working with just any real vector here. We want it to be a one-hot vector, so zeros and ones. And so to represent them correctly so that all of our inputs X come out as a one-hot vector, we use the softmax activation function, which basically makes these vectors into one-hot vectors, and then, oh no, it doesn't, sorry, it doesn't make them into one-hot vectors. It turns them into probabilities rather than unconstrained numbers. And then you've got a vector of length 10, with each entry being the probability of it equaling of the handwritten digit being equal to that value. Butchered that explanation, but then you choose the one with the highest probability. So you choose the biggest number in the vector as your answer for the digit. To train the network, we look for coefficients or weights that minimize the negative multinomial log likelihood, which is a bit of a mouthful. So cross entropy, which looks like this. So you've got a y log f of x, and f of x is your like approximation to y. I think somewhere earlier we had entropy being p log p. So my justification for calling this cross entropy is because it's rather than p log p, you've got like a p log q. So it's between something like crossing. Then in the rest of the chapter with the rest of this section, they compare this. Let me just switch back to that. They basically compare this model to a multinomial logistic regression model, which is something we've seen in earlier chapters. What surprised me here was that I thought multinomial logistic regression did pretty good. 7.2% test error. It's not amazing, but I didn't think it would be that good, basically, for the number of like parameters that you have in logistic regression compared to a neural network. Yeah, but we could see that even relatively straightforward networks with some regularization, which we'll discuss next week, gets a really good error, 1.8% test error or 2.3% test error on these handwritten digits.
Is there a sense also of like the absolute difference in the test error isn't so high, but like the multinomial logistic regression is making 4 times, my maths might be bad there, but like 4 times the error rate of the neural networks as you get closer to like, 1% error and then like 0.5% error and stuff. Like the absolute performance, yeah, it gets a lot harder, and the absolute performance isn't so different, but like the actual encountering of errors is like, yeah, it feels quite different when you actually like look at the outputs when you get that kind of difference in the error rates.
Yeah, I think that's a good point. I'm reminded of like reliability, where like 99 out of 100 is miles away from 99.9 out of 100.
Yeah.
Relative amounts of error. Yeah, 10 times as many errors.
One, you did sort of skirt over, but this, I didn't also get what it really meant by like, if these are all separate quantitative responses, like, what is it saying? Like, if this was a completely different problem and you were doing a regression problem almost, like, and you had separate quantitative response, I didn't really get what they even like meant by that.
So I think there's no constraints on the output in your network to produce numbers between 0 and 1, or to produce like one hot like classifier.
Yeah.
So you need to design a function at the end that basically turns whatever numbers you've got into a probability.
Yeah, okay. That's actually that does bring something up just from years ago reading like the perceptron paper where like they didn't know how to like have these things like layer norms that later make sure you've got like 0 to 1s and stuff. And like you basically couldn't calculate the gradients and you couldn't like solve any real problems with this stuff because like you couldn't actually make it work. But in the digit case, it would be saying like if your scores were like the number 7 score is like 17 and the score for the number 4 is like 16, it would be saying like just make the prediction 17 and like take the highest value, and that would be your like classification.
Yeah.
Okay, yeah, it's not like talking about if it's a regression problem. Okay.
Yeah, I think it's just forcing your outputs into 0, 1. Because like I think that approach that you said there, like if it was going up to 17 or whatever, that would work as long as they were all greater than 0. Because then you've still got a probability, but you're on 0 infinity. That wouldn't quite work.
Well, you wouldn't have probabilities, right? So like the idea is that you do want probabilities. But they're saying like if you had just these random like quantitative responses, it's like you just take the value as the prediction, and presumably you take the argmax of like that function that generates the value. But what you want to happen is you want like if you've got one label you're allowed to assign for 10 classes, you want it to look like a probability distribution, or you want it to follow some of like follow the probability theory like axioms about what is a probability or not. Maybe it's too much to dive in, but this always rankles me. Like I can never quite agree that soft maxed output is actually like a probability. But that's probably something for a different day.
I think you could do the first one's like, does it always give a value that's bigger than 0?
Mm-hmm.
It's because you're doing an exponential, and the exponential of anything, of any real number, is going to be positive. Does it sum to 1?
Mm-hmm.
Yeah, sum that across m.
Yep.
Because of the denominator, it's going to equal 1.
I totally agree. It follows like the form of a probability. Like the output aligns with like the axioms that are important in probability theory.
Yeah.
But interpreting it as what or like a human kind of understands as like a probability, I always find a little bit tough.
Okay. But like, why does it work, forcing it into that range?
Yeah, almost like not why even just is it just something else, but we just like to think of it as a probability? Or is it actually like some kind of, is there really any representation where it's like, okay, if I put if my softmax output is 0.6 for the digit, like a good model should get that it should assign it to that class, and 6 times out of 10 it should actually be that class when it does a 0.6. And you measure like the calibration later on and stuff, and you say, okay, like the model's calibrated if like that's happening. But is it like actually a probability? Like if you've got 2 very high scores for one class, but one of the scores is quite a lot higher, your model's kind of saying like both of them do actually kind of look like the class, or like each class, but I just have to pick the one with the highest score. Yeah, I probably haven't expressed it very well, but I always just find that the softmax stuff always just feels like a little bit of a hacky way of like making stuff look like a probability that we then want to interpret in the same way. Like if a person says, oh, I think it's like 90% likely that Sinner beats Alcaraz, you know very clearly that they think 9 times out of 10 Sinner would win, and they've based that on like how they think about Sinner and Alcaraz or something. Whereas in this, it's like there's just a score for each individual one about whether it kind of looks like something that belongs to that class. And then we just come along, add the softmax and go, look, now it's probability.
So is your question, why is this a probability?
Yeah, like in what sense of the word, like, or as like most people kind of understand probabilities, like in what sense of the actual thing we try to talk about when we talk about probabilities is taking these scores from all of the hidden layers and then just like running through the softmax and getting a bunch of scores that add up to 1 and all of between 0 and 1. In what sense is that actually really like a probability or like a probability estimate?
Yeah, that is a good question. No. I'm sort of trying to think of it from the opposite angle. Like if I have a vector that sums to 1, all the entries are between 0 and 1, is that always a probability distribution? Or could that be interpreted as a probability distribution in the right context, I guess? It's the context that makes it different, isn't it?
I would say it is always a probability distribution because it fits the axioms. But there's also the other answer is true. Like it is actually, in my mind, it's really dependent on the context. So that's like a good way.
Yes, it's a probability measure, but a probability measure of what? How do you prove that it is measuring the probability that you think it is?
Yeah. And I guess your loss function kind of does it over time if the probability output is like high. So like, and you know, it's wrong. It's like, well, the gradients now are going to be quite big to adjust the other way. So I guess in the context of the whole network, maybe it does start to like resemble a probability. But equally, there's this other thing where like your loss is going up. Say if you want it to go down, your loss is going up, as in like when it makes an error, they're really bad errors. But your model's actually getting better at, say, accuracy. And what's happening is it's just getting overconfident in its predictions. So the loss is like looking like it's bad, but actually the model's getting stronger at what you want it to do. But again, that's maybe a tangent.
Very interesting, though. I think that's the fun part of the book club, is that it doesn't have to be a lecture. So I always appreciate okay, where we're up to, we've got multinomial. So we're comparing this multinomial logistic regression with the neural network, and the logistic regression that they fit has 7,065 parameters with a 7.2% error, and the neural network has 235,146 parameters. So to avoid overfitting here, there's got to be some regularization going on, which again we'll come to later in the chapter. That was my other feeling in the chapter, is that if you don't know what regularization is coming in, they just say we'll talk about it later quite a few times. But it doesn't really help. But yeah, your number of parameters is 4 times the amount of training data, because you've got like 60,000 images, was it? I can't remember. 60,000 training images, and 240,000 parameters. Okay, so that was the intro to the section on neural networks. So we've nearly finished the hour. So I'll just briefly run into CNNs, the convolutional neural networks, in the last 4 minutes.
Do you want to do it today, or do you want to put it off the next week?
I'm happy to just stop there, to be honest. I think we're not going to get very deep into this section in the time.
Yeah, and I think maybe, so off for people on YouTube, we sort of discussed whether we would do a 3rd week for neural networks. And I think based on this session, yes, we probably could or should. What do you guys think?
I'd be keen to.
Yeah, I'd do that too. Yeah, if we can at least find like a appropriate reading for it. Or would it be from this chapter still, or we'd add extra material?
I think extra.
Okay, yeah.
Just try and find. I think I've found a few references on like intros to attention mechanisms and transformers and things. So there's like an illustrated transformer that I haven't had a chance to read through yet, but it comes up quite a few times in intros to it, which I think could be good to see.
The JLMR blog post.
That rings a bell. Is it the one where it's like, this is now a book at the top?
Oh, sorry, there's the illustrated transformer, there's maybe the annotated one. There's one on Harvard that is a really good resource as well. And then there's a blog series by JLMR, and they're actually, yeah, they're both really good resources. I'll stop the